Hello, and welcome everyone to the next event in our webinar series, a presentation by returning Thorlabs expert, Jens Küchenmeister. My name is Mike DeArmond, and I'll be moderating today's talk. Dr. Jens Küchenmeister is the leader of Thorlabs Educational Products Business Unit. After studying physics and math, he received his PhD from the Karlsruhe Institute of Technology, Germany, where his doctoral thesis focused on the numerical solution of Maxwell's equation in nanostructured systems. His high motivation for teaching physics, demonstrated by numerous voluntary teaching assignments, led him here to Thorlabs, where he has been growing the educational business unit since 2013. Throughout this talk, please feel free to submit any questions you have using the Q&A tool. Jens will be answering any of those questions at the end. With that, I'd now like to hand it off to Jens.
Thank you for the kind introduction and welcome from my side as well. So today I would like to show you three things. First of all, I would like you to gain an intuitive understanding of what polarization entanglement is all about. Secondly, I would like to show you how to set up an entangled source in the lab. And then I will talk about experiments that you can do with entangled photons. Now, entanglement is a quantum property you can achieve in different systems, for example, electrons. Today we're going to talk about entangled photons, specifically polarization-entangled photons, meaning whenever I talk about entanglement today, I specifically refer to polarization entanglement. You know the property of polarization from a classical electromagnetic wave, and you find the same for single photons. Please excuse me for just having this little dot here as a representation of a photon. The way that we write this down is in this ket notation here, so a vertically polarized photon would be V. Now we're talking about photon pairs throughout the presentation, so two of those, we write this down if we have two vertically polarized ones as VV, and similarly if we have horizontally polarized ones with HH. Now let's look up what polarization entanglement is all about. So you open a textbook and what you see is this. So you have HH plus VV and some kind of normalization. Now, if you're anything like me, that doesn't really help you much in terms of understanding what's happening. So rather than going through this mathematical representation in too much detail, I would much rather show you how this entangled state is prepared in real life and what that implies. And the first thing that we're going to do now is we're going to look at how to create photon pairs. This happens through a process called spontaneous parametric down conversion. So you have a nonlinear crystal. In our case, we talk about BBO today. You shine a blue pump laser on it, and you're generating two photons at 810 nanometers. Now, the BBO today that we're talking about is so-called type 1, which means we're generating correlated pairs, not yet polarization entanglement pairs. We come to that later. And correlated is basically just a fancy way of saying it's a pair. Now, let's look at this in a little bit more detail. So we have our nonlinear crystal here. We have a blue pump laser oriented in horizontal polarization. And if the crystal and the pump fulfill certain conditions, you're generating photon pairs. And as you can see here, the polarization of the pairs is perpendicular to the pump. So if I'm coming in with horizontal polarization for the pump, what I'm getting out is VV. Now, this doesn't just happen in one direction. This is a symmetric problem. So in fact, I'm not only getting two, but I'm getting a cone of photon pairs. Next up, we're looking at how to create entangled photon pairs. And one way to do it is to take two of those type 1 BBOs, you rotate one by 90 degrees and you put them together. So let's look at what happens for different pump beams. If I have the same pump beam as before, so I have a horizontal pump beam, then I face my first crystal, I'm generating the VV pairs that we saw on the previous slide. Now, what you just have to trust me on is that if I'm sending in the horizontal polarization onto this crystal that is rotated by 90 degrees, then simply nothing happens. Next up, we're rotating our pump polarization. So we now have vertical pump. The first crystal doesn't do anything, but we're generating photon pairs in the second crystal. So these are then polarized in HH. Okay, now you may already see where this is going. If I'm now rotating my pump polarization by 45 degrees, then I can generate pairs in both crystals. Now this is already a danger for a misperception. What you might think now is what happens when I'm sending in the pump light is that I'm just generating pairs at random. So, right, just a random assortion of HH and VV polarized pairs just coming one after another. This is something that you can prepare as well, but this is something that we would call a mixed state. This is not entanglement. So the question is, what is entanglement then? How do I have to picture the physical reality of what's happening here? And it's not so easy. And in order to describe it better, I would like to take a little detour, namely through a Michelson interferometer. Michelson interferometer means you have light shining onto a beam splitter, half goes to mirror 1, the other to the second mirror, it comes back, and when I'm recording what happens at the output, then I'm seeing this interference pattern here when I'm moving one of the mirrors. Now, crucially, the same is true for single photons, right? So if I'm sending in single photons one after another, then I record the same output behavior. And this is where sort of the questionable picture of this little dot flying around from a photon, this is where this breaks down, because it just doesn't behave like a little dot, it behaves like a wave itself. So if I'm asking the question, which path does a photon take, which is already a bit questionable of saying it like that, but the proper answer would be both, right? So even the single photon sort of sees both paths in the interferometer, meaning that at the output of the interferometer, the photon can only be described as a superposition state of path 1 and path 2, and this is what creates the interference. Crucially, the interferometer output signal just cannot be explained without this superposition, so you must not picture it as just one dot going somewhere. And if you've understood that, this really helps to understand what's happening in our crossed BBO. So let's apply the same principle to the crossed BBO. In my interferometer, what I said is I must not picture a photon just taking one particular path through the interferometer. Similarly, for the cross type 1 BBO, I must not picture the pump just generating a photon pair in one particular crystal. So in the interferometer, we said that one photon just basically sees both paths. I can't describe the experiment without the superposition of the both paths. And the same is true for the cross type 1, meaning my pump light basically sees both crystals at the same time, and I can only describe the outcome of my experiment when I think of this as a superposition of photons being created in one and photon pairs being created in the other crystal. Crucially, the paths here need to be indistinguishable, right? So if I do anything that makes these paths distinguishable in the interferometer, then my interference breaks down. Similarly, the pairs coming from the crystals, they need to be indistinguishable. So what you do in practice is you change the angles of these crystals here, which dictate basically the opening angle of those individual cones, and you need to overlap them very well so that really there's no way to distinguish where the photon pair sort of came from. And again, we need to get rid of this sort of specific crystal, where does it come from? That's something that we need to get rid of. So at this point, just a brief summary. If we have an entangled state, we don't have defined polarization. We have a superposition. We have a superposition of these two possible states, creation in crystal 1 and creation in crystal 2. And importantly, this is really not a lack of knowledge. So this is something that is often misinterpreted. It's not like that we just don't know which of it is. It's really that you cannot describe the system behavior without picturing this as a superposition. And at this point, you may still think you're being very vague because I've never described what system behavior actually means. You're completely right, and I will show you in a few slides so that we can actually talk about differences between entangled states and mixed states. Before we do, We need to look at what happens at a polarizer though. So again, we have our pair crystal. We're creating this entangled state that we talked about before. And now I'm placing a polarizer here with a 0-degree angle. So what happens? Well, it's basically a 50-50 decision, right? So either the photon, we have our VV plus HH, and either I will pass, the photon here will pass the polarizer or not. If it passes, then by definition, it will have a vertical polarization as well. And the crucial thing what happens is, as I said, we just have VV plus HH. So if the first one is measured to be vertical, then the second one has to be vertical as well. So the measurement on the first one defines the polarization on the second one. And importantly, this doesn't actually have to be measured. So I don't specifically have to measure it at that point, but every experiment that I will do with this photon will behave like a photon with a vertical polarization. Now, it won't surprise you when we're turning this on its head in the sense that we have the 90-degree polarizer, we still have VV plus HH. And so again, if the first photon passes the 90-degree polarizer, it will be horizontally polarized. And again, if my first one is defined, the second one is defined automatically as well. Now, the next thing may be a bit less intuitive. So what happens when I have a polarizer with a certain angle? Well, then either the photon here will be transmitted or not. If it is transmitted, then it by definition has to have the same angular orientation as the polarizer. But now what happens with the second one? And the answer is, again, if you define the first one, the second one has the same polarization. This is not super intuitive, I would presume. If you write that down in this like half a page of calculation, then you see that this is true. You can find that in our manual. For now, you will have to believe me that if I'm measuring one to be in phi direction, sort of say, the other one is automatically in phi direction as well. Now, finally, you were at the point where I have to give you an example to understand where a system behaves differently for entanglement. It looks quite similar to what we had before. So we have our photon pair, but now we place two polarizers here, both with the same polarizer angle phi. And the question that we're asking ourselves, what is the probability that both photons pass through these matched polarizers? So let's look at this. Let's look at what happens with an entangled state and what happens with a mixed state. If the polarizer is oriented in phi equals 0 degrees, well, then basically it's like a 50-50 decision whether or not the system decides to be in vertical or in horizontal. So we have a probability of 0.5. Because if the first photon here passes through the first polarizer at 0 degrees, we said before, then the second one automatically has 0 degrees too, so it passes through the second one automatically. Now, what happens for a mixed state? Well, if my polarizers are 0 degrees, then all of the vertical ones are going to pass, all of the horizontal ones are going to be absorbed. So the chances of finding both of them passing through is again just 50-50 because all of the HH pairs will pass through. Now, just due to symmetry, it's the same thing for 90 degrees. So again, we're going to have 0.5 for the entangled state and 0.5 for the mixed state because all of the VV pairs will pass through. Now let's look at the 45-degree orientation. This is where it becomes interesting. So, as I said before, if the first photon passes through of my entangled photons, then the second one automatically has the same polarization. So if the first one passes, where the probability is just 50%, right? Just for symmetry reasons, if I have a 45-degree polarizer, then the probability of it passing is 50%. But crucially, if that one passes, the other one has the same polarization. So again, it's a 50-50 decision. It's 0.5. In comparison, what happens with the mixed state? So just assume that I have two vertical photons arriving at my 45-degree beam splitter. But if they're not entangled, they don't know about each other. So each individual photon makes a random decision at its beam splitter, at the 45-degree beam splitter. And each of it is going to pass or not pass. And so either both can pass, or both can be absorbed, or one passes and the other doesn't, or vice versa. So in the end, the cases where the mixed state, the probability of the mixed state both passing through is just 25%. And when you're plotting this over all angles here, so what I'm plotting here is the coincidence probability over the polarizer angle. You can see that with the same argument as before, the entangled state shows constant probability of passing through, while the mixed state shows this behavior here. So that's the first experiment, and we'll come back later to actually show how this behaves in a real experiment. You can see here the difference between a mixed state and really entangled photons. Now, I hope now that you have a bit of an understanding what polarization entanglement is about and how to create entangled photon pairs. Then I want to show you how you can set this up in your lab. Well, I wouldn't be here today if I didn't have a good solution for you, namely our Quantum Optics Kit together with our Polarization Entanglement Extension Kit. These are part of our line of educational kits. If you're not familiar with those, we have these just to excite the next generation of students to go into the field of optics, photonics, and quantum optics. And we try to make it as easy as possible for the educators, so we write up really extensive manuals. They are free for download, so even if you're not able to purchase the kit, you can easily just download the manual and use all of its content for your teaching. Secondly, the kit price is just the sum of the components, meaning all of our research and development effort, writing up the manual, writing the software, all of that is not reflected in the price, which makes this really good value for money. Now, I have to, before I get into the details of what this entanglement extension kit does, I will have to get you up to speed of the Quantum Optics Kit itself. So here's a very brief review. So you see the setup from the side. We're starting down here with our blue pump laser, over two alignment mirrors to our nonlinear crystal. That's the BBO type 1, so not the double crystal, but just one type 1 crystal. Once the pump beam has passed through the crystal, we don't need it anymore, so we collect it down here at a beam dump. As we said before, the photon pairs are generated in the crystal, so we collect them here with two single photon detectors. For some experiments, we introduce a beam splitter and guide the light, for example, to this Michelson interferometer, at the output of which there is a third detector. Now, all of the data correlation measurement is done through an education grade time tagger. So all of the signals coming from the single photon detectors go into this box, which is essentially a very precise clock, and that does all the correlation of all the signals. The kit also comes with a number of alignment tools, because for us it's always very important that students can set this up themselves. So there are a lot of cool tricks that we implemented here to make sure that such a complex system can actually be aligned well. Now, this is something that you've seen before. This is our little sketch. What happens, the way that we're measuring this, as I said before, are single photon detectors, but the question has to be asked, how do I identify a pair? And that's simply done by timing, meaning if my detectors T and A click within a certain coincidence window of just a few nanoseconds, then I'm counting this as one event. So this was most likely the pair. Now, in contrast, when detector T clicks and like a millisecond later detector A clicks, then it was probably stray light or dark count event or something else. So we're not counting that. And now you get the picture of sort of how I get my photon pairs and what I'm counting. Now, I don't have time to get into too much detail for the Quantum Optics Kit itself. Just know there's a webinar that you can look at. Either you find it through our webinar series or just on the product page of the Quantum Optics Kit itself. And in it, I describe in detail what you can do with the kit. For example, you can distinguish between a classical and a non-classical light source with a measurement. We address misconceptions. For example, students often have this misperception that an attenuated laser is a single photon source, which you can experimentally verify that it's not. We do the single photon microsynth interferometer, we do the quantum eraser, and you can even turn this into a 2-qubit optical quantum computer. But now, without further ado, let's get into the polarization entanglement extension. And if only it were that simple, just to take the setup and just to drop the cross type 1 BBO in here. Well, life is rarely that easy, and I will show you why in a second. Primarily, what you're creating with these crossed BBOs is not HH plus VV, but HH plus a certain phase term here plus VV. Now, what is that phase term? That depends on two things. First of all, the detection angle. And before I always had these little arrows showing what happens with the SPDC. It's not that easy. SPDC happens in more than just one straight direction. And so rather than just having one straight line from the crystal to your detector, you collect more light. So when I'm going back here, so I'm starting from the detector chip, I have a focusing lens in front of the detector chip here. So I'm collecting a lot of light coming in from different angles. Basically the minimum and maximum acceptance angle is defined by the detector aperture. And it's very intuitive, right? A different angle means a different phase up here. Secondly, my pump laser does not have just a single frequency, simply because, single frequency lasers are expensive, and in an educational experiment, we just use a simple Fabry-Perot diode. Now, there are ways to conquer the effects of those two. Crucially, what you have to understand is you still never get to zero phase delay here for all pairs that you are measuring. So in practice, what you have to do is you have to reduce the range of those phases as much as possible. So you're always going to collect pairs with different phases, but the point is you have to reduce that phase range as much as possible, or else your entanglement will not be observable. So I understand this is rather technical on first sight, but it's very important in a lab context. So let's look into this in a little bit more detail. So as I said, the spontaneous parametric down conversion, so this pair creation, happens across different wavelengths combinations. So what I showed you before is not the entire truth, because apart from 810 and 810 being created together, you're also generating 811 and 809 and so on. And crucially, due to the momentum conservation, they have a different angle at a different emission angle. Now, different emission angle means different phases again, right? Because a different path, especially since we're going through these nonlinear crystals, we're collecting different phases. All of this is called spatial walk-off, and we can fight that through different means. First of all, the simplest one would simply be by reducing the detector aperture, right? So if I'm closing the iris in front of my lens that focuses the light onto my detector chip, the acceptance angle becomes smaller. But practically, I don't really want that, because I'm basically just cutting off count rate, and count rate is always the thing that's problematic in quantum optics experiments. Secondly, what I can do is I can just use thinner crystals to minimize the walk-off. The problem is that you will need to compensate for that with higher laser power, because the count rate scales about quadratically with the thickness of the crystal. So making it thinner will mean you have less photons, and if you want to arrive at the same count rate, you will have to increase your laser power significantly. And 200 milliwatts of blue in a lab are not so much fun. The third thing that you can do, what is often done in labs, you basically choose additional birefringent crystals that you place in the beam that have the reverse effect. And so these are the two spatial compensation crystals that you place in the setup that counter the spatial walk-off. Now let's look at the other thing that we talked about, that the pump laser spectrum is just not one line. Now remember, we have to go through this dispersive birefringent crystal with our pump laser, and so different pump wavelengths will see different optical indices in the crystal, again giving a walk-off, and this time it's called a temporal walk-off. Again, there's three ways to combat that. First of all, the thinner crystal version, which we already ruled out because of the count rate and higher laser power. You can use single frequency lasers. They start at like 3 to 4K, but for an educational experiment, you don't want that. And so what you do in practice, again, you introduce another birefringent crystal that does a pre-compensation, again with the reverse effect of the temporal walk-off. Now the next note is for connoisseurs. You also need one optical element to set the global phase, meaning, there has to be a way how I get from HH plus VV to HH minus VV. And so you can do that with an additional optical element. We basically, for simplicity, use the temporal walk-off crystal for that as well. So we can just tip and tilt that, and then you introduce this, you can change this global phase. All right, so now we have all the ingredients that we need to experimentally generate our photon pairs. So we're replacing the type 1 BBO with the cross type 1 BBO. We're placing our temporal compensation crystal before that. So we come from down here with our blue pump laser, going through the temporal compensation first, then into the cross type 1. Then the photon pairs go through the spatial compensation crystals. And now we have our entangled pairs. Crucially, the alignment procedure of the quantum optics kit stays the same. So if you're familiar with that, as I said before, we put a lot of love in there so you can systematically align everything. It stays exactly the same as it is even with these cross type 1 crystals. You don't have to put a lot of work in to get from one to the other. That's the next great thing. So if you've done this a few times, you can just really switch between the quantum optics kit and the entangled photon pairs in like 5 to 10 minutes. If your students do it for the first time, it's maybe half an hour to an hour. Okay, so let's look at experiments that you can do now. And the first thing is the introductory experiment that we've seen before. So we have our entangled pairs, we have two matching polarizers, and this is the plot you've seen before. So the coincidence probability of the photons passing through the polarizer is constant for entangled photons, and it wouldn't be just for mixed state. And so what do? Well, you do exactly that. So you place two polarizers in front of the detectors, and those are the two other optical elements that you may have asked yourself what these are. So those are the two polarizers that are also in the extension kit. And now you simply rotate them by the same value. So you have them like this, and then just go through with the same value, and you will see that the coincidence rate stays the same throughout every rotation, which already is a great introductory experiment to see, okay, this is something that just doesn't happen in classical physics. Next up is Bell's inequality, and this is certainly something that is sort of the most complex, but one of the most cool experiments you can do with entangled photons, just because it's so much physical depth to it. Now, let's assume that I have an entangled photon pair, and I send one to Mars and I send the other one to the moon. The crazy thing is, when I do the measurement on Mars, so I have my polarizer with orientation phi, and I'm measuring, and my photon state decides, okay, I'm phi, then the photon on the moon is also in phi. And that's sort of crazy because it kind of has to be instantaneous, right? We didn't actually talk about any kind of direct interaction between the two. And this is something that people felt at the beginning of when quantum physics was introduced, felt very weird about, and Einstein famously talked about spooky action at a distance. The good thing is, it doesn't violate general relativity because there's no possible way to transfer information, because nobody, if I'm on Mars, I didn't know if the person on Moon already did the measurement or vice versa. So I don't really have a way to transfer information. And don't we just live in a great time where you can tell an artificial intelligence to create a spooky Einstein with Mars and the Moon in its hands? Okay, now crucially, Einstein and others, they had really big problems with this instantaneous aspect of it, because they felt like a proper physical theory should have two very basic things. First of all, it should be local, meaning that if I measure a specific object at a specific site, then the outcome of the measurement has to be defined by the features of that object at that site, and not of another object somewhere on Mars. Also, they felt like the physical theory has to be realistic, meaning that all measurables have to have definite values at all times, even if I may not know them. And just to give you a better feeling of what that means in contrast to an entangled state, picture two boxes. Picture a pair of gloves, and I'm putting the left one in this, putting the right one in this box. I'm closing down the boxes, I'm shuffling the boxes, and now I give you one of the boxes. I have the second one. You open your box, and immediately by looking at your glove, you know what I have in my box. So these are correlated. This is a correlated system, right? You know what you have, immediately you know what I have. But it's sort of a classic correlation, it's not entanglement, because crucially, the point is that the glove was always in a specific box, and at all times it was defined which box had which glove. In contrast, an entangled state, as I said before, is just not defined until you make a measurement. And this is something that they were very unhappy with, and in essence, they said, okay, quantum mechanics has to be incomplete in some kind of way if that's what comes out, if the spooky action at a distance is what comes out of quantum theory. But there was no way to determine who was right, and it took a really long time, namely until John Bell came along, and he was able to formulate an inequality that holds for all local and realistic theories. And it sounds very abstract, and it kind of is, but the point is he was able to write down an inequality, and people knew that, all right, once I have designed an experiment that violates this inequality, well, then I've basically proven Einstein wrong, because, well, either the system is non-local or non-realistic. And again, it took a while until people were able to do that, and famously, entangled photons were the first systems that showed this violation. When you do it for entangled photons, then Bell's inequality is translated into the CH-SH inequality, named after those four people here. And if you know the name Clauser, well, famously, he won the Nobel Prize a few years ago for his experiments with entangled photons, establishing the violation of Bell's inequality. Now, how does this look like in the experiment? We don't have to change anything. Everything is there already as we need it. We have our two polarizers in front of our two detectors. And what we have to do now is we take 16 different measurements at certain polarizer settings. Now, in preparation for this webinar, I spent literally hours scouring the internet for some kind of nice explanation, some nice visual to tell you what's going on. I didn't find one. So at a certain point, I fear that we have to just acknowledge that the quantum physics just isn't always easy to explain. It's a lot of math, and in the end, it is what it is. So what you have to do is you, as I said, have those different polarizer settings. What you see here is a screenshot of our software, and you have this 4x4 matrix where on the one axis you have the upper polarizer setting, on the horizontal axis you have the lower polarizer setting. And what you calculate from these values, so you're measuring for a certain time, and you're measuring these coincidence rates, so how many photon pairs arrive at the detectors, and then from those rates you calculate so-called S value. And you can see here you give that by, it's given by some E values, and those E values are calculated by those colored count rates we had before. And just as an example, so this green one here is calculated by all of those different ones. Again, don't even try to picture something happening there. Now, when you do all this theory behind it, what you see is that if you calculate this, there's a classical limit that all classical theories have to abide by, and that's 2. So you will never get a value larger than 2 in a classical setting. But if you have a perfectly entangled state, you will see a maximum value of about 2.8. And now in our software down here, we have calculated the S value from all of those, and it's about 2.6, meaning yes, we've actually shown that Bell's inequality is violated, and well, entanglement is real. Now, once your students have sort of worked through that and sort of bathed in the profoundness of this, then you can look into more aspects of the system, right? So you can, for example, look into the compensation in more detail. And for example, what you can measure is what I'm showing here, the S value measured for different iris apertures, meaning so different openings of the detector. And as you can see here, when all of the compensation that we talked about is in place, then the S value hardly changes. So I'm opening my iris, I'm collecting more photon pairs, the S value hardly changes, it stays at about 2.6. Now let's do the same thing without the spatial compensators. So let's analyze this walk-off. And so again, I'm plotting the S value over the iris aperture, but this time without the spatial compensation crystals. If I close the iris down to really just 3 millimeters, I can still measure an S value above the classical limit, but I'm opening it more, I'm collecting more and more photon pairs with different phases, and there's at a certain point the phase range just becomes too large, and I'm going back into this classical regime here, and my entanglement is no longer visible. So that shows that all of the things that I talked about previously, that the walk-off, that's really important to consider. Next experiment is called state tomography. If you don't know what that is, well, essentially you can't just measure the state of a photon or a photon pair with one quantum measurement. What you have to do is you have to prepare your system in the same way multiple times and do multiple different measurements to reconstruct the entire quantum state of the system. And that's what state tomography does. Now, if you want to do that with your students, to be quite frank, it's a bit tedious and technical, but it's a really important real-life tool because, whenever you see a publication where people prepared entangled photons, they will want to prove that they achieved good entanglement. And so they will do a state tomography. And what you see then is this kind of density matrix visualization. Again, I'm not going to go into detail here, but it's basically just a visualization of what your entangled state looks like, or generally your photon state looks like. In order to get something like this, experimentally you don't have to do much. So we keep the arrangement as before. We have our 2 detectors here, we have our 2 polarizers, and now we add 2 quarter wave plates, and that's basically all. These are not included in our extension kit, so this is why this is sort of just an additional experiment, but we describe that in detail in the manual. Now, if you have an n photon system, you need 4 times n squared measurements to get the full tomography. Since we have 2 photon system, we need 16 different settings. Even though this is the parts are not included in the extension kit, we already have that in the software because we assume that a lot of people will want to do that. So you can do your different measurements with those different settings for the polarizers and the quarter wave plates, and then you will get your state tomography result. And then you can the fun thing is that you can start to prepare different entangled states, for example, HH minus BV, which looks different, or even states that are not entangled. And so you can see the difference. Now that brings us to our last experiment, quantum key distribution and the E91 protocol. So if you haven't had exposure to quantum key distribution yet, or quantum cryptography, it makes sense to look at the sort of simpler case of single photons first. So there are different protocols for quantum cryptography. The first one that was developed is called BB84. It's with single photons, and we have a really nice educational kit for that one. So you have a sender Alice, you have a receiver Bob, and crucially, the point of quantum crypto is when you place an eavesdropping party Eve in between, then her measurement of the system is inevitably changing the outcome of the quantum measurement, meaning that her presence is revealed by Alice and Bob. If you want to look at this in more detail, there's a webinar. Again, when you go to the kit's page here, you can look at the webinar to get a better fundamental understanding of what quantum key distribution is about. I don't have too much time here, so excuse me that I'm rather brief. Now, it took a while, but in 1991, Arthur Eckert came along and he says, well, can we use this property of entanglement also for quantum key distribution? And he created the E91 protocol. And the idea is that if I have an entangled pair, then Eve's measurement will automatically destroy the entanglement, and there's no way that you can just bring that back. And so this is how her presence is revealed. Now let's look into this in a little more detail, what the protocol is about. Now assume you have your entangled photon source, so that's the red box here. It sends out entangled photons. Again, I'm sorry for the little dots flying around, but you know what I mean. The first step of the protocol is that Alice decides for a basis, meaning she either measures in polarization basis plus or crossed. In this case, she measures in the plus basis, and the photon basically decides to say, okay, I'm horizontally polarized. Then we talked about this at length now. If the HH plus VV polarized or entangled state, if Alice measures the first one to be horizontally polarized, then the second one is automatically also horizontally polarized. And now when Bob makes a measurement, again, he can decide for either plus or X basis. If he chooses the plus basis, then, well, as we said before, the horizontally polarized photon will just pass through. So he will measure the same bit as Alice did. If he chooses the crossed basis, well, the result is random. And so later on in the protocol, these measurements are just discarded. So Alice and Bob talk about their choice of the measurement basis, not about the bit they measured, but about the choice of the basis. And all of those measurements here are thrown out because the result is random. Now, the ones that they talk about, they know that they had the same result because of the entanglement. And so they use those bits as the encryption key for their communication. Again, I know it's quite fast. Just look at the webinar from the quantum optic, from the quantum crypto kit. Will give you a better understanding of what I'm telling you here. Now, let's look at this experimentally. So you see there's a different arrangement over here. So let me start out at the bottom so we can work our way through this. So again, I'm starting with my blue pump laser. I'm going through my temporal compensation crystal. I'm going through my crossed type 1 BBO. I'm generating my pairs that go through the spatial compensation. And now you can see here, now I have 4 detectors, 2 symmetrical arrangements, and they're symmetrical because essentially one of them is Alice and the other one is Bob. Now let's zoom in a little bit. What you see here is a polarizing beam splitter. So we can separate the different polarizations. And there's a half wave plate, which allows for the basis choice that I just talked about. Now again, those parts are not included in the extension kit, but we describe all of the protocol in the manual. We describe all of the parts that you need in the manual. And now the cool thing is that the students can really play through this protocol. You have to picture it like that. Each student has its own keyboard and PC screen, because again, we already implemented that in the software for you. So what Alice sees in her screen is this. Bob similarly sees this screen. And now what you will want to do is to have some visual block between the two. So you either have a little curtain or a piece of cardboard or whatever. And then the two of them manually set their bases by just rotating their half-wave plate. The software just collects one coincidence event, so really just one pair. And then they do that over and over again until they have collected enough events. They do this basis exchange so they can throw out the ones where the measurements where the bases didn't match to generate their key. Then they can encrypt their message, transmit their message, and decrypt it. So they can really play through the entire E91 protocol with entangled photons. Now, that brings me to the end of my talk. So what I would like you to take home. First of all, if you're thinking about generating entangled photon pairs, always think about this in terms of these two crystals being one after another, and you have a superposition of those two crystals generating pairs. It's not one or the other, it's a superposition of both. Then, if one photon is measured, the polarization state of the other is determined, right? So we have the specific example of those photons where I measure it in phi, and my other one then automatically has phi as well. If you want to set this up in your lab, there's quite an easy way to do it through our Quantum Optics Kit and the entanglement extension. And quite importantly, I really enjoy people sending feedback. So we have quite an interesting community with the educational kits. So there's people coming to me all the time talking about extensions or different experiments that they've done with the kits. And we like to include those in the manual as well. So please feel free to reach out, any kind of feedback. We're always happy about to improve the manuals or to add new experiments. All right, so that concludes my talk, and I'm looking forward to your questions.
Yeah, that was great. I had kept an eye on the release of this, and I'm happy to see that it's live. We do have a few questions. We'll get to as many as we can. Please feel free to drop them in the chat as they occur to you. Jens, to get started, I guess we'll start at the beginning, going back through the presentation. You mentioned that this is all in the context of polarization entanglement. What other sort of properties can be entangled and could, in principle, be investigated in a similar way?
Yeah, okay, so there are different ways to entangle photons. There's time-energy entanglement, there's orbital angular momentum, and there's path entanglement, which is kind of one of the more common ones when you're thinking about photonic quantum computers. These are always those nested interferometers, because essentially, you're entangling path information there. At the moment, we don't plan on adding something like that. I mean, as I said, we have this 2-qubit quantum computer implementation already, where you can kind of play with that. I don't think that we're going to look into other kinds of entanglement in the foreseeable future.
Fair enough. I think this is a great start to the entanglement add-on to begin with. So there's plenty here for customers to work with. And I don't know that you mentioned it, and I'll mention it explicitly. I think it's the link is posted. This is live on the website, so this is a released product. So if anybody wants to find the full details, including pricing information, availability, and the manual, please do check out the website. A couple of practical questions came in, Jens, just regarding the setup, and maybe you could speak to some of the customer feedback you've gotten and feedback from students as they learn how to do these. Can you discuss a little bit about the practical considerations for setting up the coincidence window, for instance, on the time tagger?
Yeah, so we just choose a window. There's no really right or wrong. So we use 5 nanoseconds. You could use 4, you could use 6. Basically, your it doesn't make too much sense to go lower or too much lower, because at a certain point you will see the jitter of your system, right? So each element has an electronic jitter. The Tiger, for example, has 750 picoseconds RMS jitter, and so just 5 nanoseconds was just a reasonable width that we found out that works well.
Yeah, fair enough. You had mentioned, you'd gone into quite a bit of detail actually, but we had a couple questions asking for more detail on the compensation for photon walk-off in particular. You mentioned the difficulties. Can you talk through a couple of those difficulties and how difficult it is to properly compensate on a system like this?
Yeah, fair enough. So you have to picture it in a way that, you know, there's so many different parameters that you can change for the compensation crystals, right? So we have this temporal one, we have our pair BBO, and we have the spatial compensators. Now, you can choose different materials. That's the first one. You can choose different thicknesses. Then you can choose different crystal cuts, which really makes it difficult. And essentially, one of my engineers spent, I would say, about 2 months going through the papers that you can find about this entanglement type entanglement crystal and the compensators, wrote a code of like 1,000+ lines, and then just iterated through different versions. We did some prototyping rounds to ensure that we really have reliable crystals, because, you know, it's always a bit of a trade-off. You don't want to optimize it just for the perfect S value. You also want to optimize it for really good alignment, and it's just working easily. You just drop it in and it works. And so we did a couple of rounds there, and we arrived at something where we really reliably get S values of 2.6. And yeah, so you can just, you know, the question comes up frequently. If you want to purchase these crystals individually, we're more than happy to provide those as well.
And I guess actually on that, as a follow-up, the thickness and the type of crystal, that is chosen to be paired with the supplied pump laser, is that right?
Yes. So, well, yes and no. I mean, in a sense, what I can assure you is that it works for our pump laser. So we have pre-selected laser diodes with a wavelength window of about 1 nanometer plus minus the 405. And so it works for that range. And as you've seen, the spectrum is not super pretty. So you've got several laser modes in there that works. If you have a different laser, let's say, I don't know, 403 or something, well, just get in touch and we can talk specifics, just how much of a deviation you can expect.
Is the crossed type 1 BBO the only crystal that can generate the entangled photons?
Oh, that's a good question. Yeah, this is actually okay. So before I answer, so the first answer is no, it is not. What you will often find in literature is a type 2 BBO. I will talk to what that means. But first, let me recap what the cross type 1 does. So the cross type 1, as I said, generates a cone of photon pairs from each crystal. So you have 2 cones, and you need to, in practice, when you're aligning the setup, you need to change the angles, so tip and tilt, to change the opening angle of the cone. And essentially what you have to do in the end is you have to overlap them well in the plane of your detectors. Now, when you have this type 2 BBO, what you have is you have 2 cones next to each other. And what you have to do is you have to basically put yourself in the intersection of those 2 cones. You're also generating a different state. So for the cross type 1, you're generating HH plus VV, as I said, or minus. For the type 2 BBO, you're generating VH plus HV. And in practice, the biggest differentiator between those two is the count rate and how well you can align it. So we had a different project with a collaborator where they used the type 1, and it turned out to be that the count rates were lower than the cross type 1 for the type 2, and the alignment was really painful. So this is why we said, even though you often see this there's a famous book from I think Mark Beck where you have these two cones overlapping, and so a lot of people ask about the type 2, but the lab reality is it's going to be much nicer with a cross type 1, better count rates, more reliable.
Perfect. Actually, that's a natural segue into another question regarding the states. So I think you touched on this in your presentation. How does the state HH plus VV differ from HH minus VV?
Yes. Okay. I didn't want to confuse people too much. So when you remember probably when I did this with my hand. So I'm measuring one photon in a phi orientation, and the other one then automatically is set to phi as well. If you have the state HH minus VV, what changes is you're measuring one in phi, and then the other is set to minus phi. That's it.
I wonder maybe you can, so since this is an add-on to the existing quantum optics kit, can you maybe share some of the feedback you had gotten from students and educators on maybe the original kit that sort of led into this development, and how to approach this development to sort of demystify a lot of this entanglement jargon to students?
Gotcha. So the feedback has been really positive. We actually got a prize from the German Physical Society not too long ago for it. And I can just give you a point of reference. So there's a professor in the US who basically gives the students the empty breadboard, and after 2 days, they've gone through every measurement we describe in the manual themselves. So they are able to align it themselves. They're able to go through the measurements themselves. And that was our biggest, design point, that we wanted to make sure that this is really, it's an open setup, but you have to align it yourself, because we feel like it's our philosophy for the educational kits. Best way to learn is doing it yourself from scratch. Now, the quantum optics kit has all those basics. So, understanding what is a single photon even. So how do I characterize non-classical light source, and how does that differ from a classical one? So we felt like it was really important to lay the foundation before going into entanglement. But a lot of people naturally ask us, can we just take a different crystal and get entangled photons? And given that it's not so easy, we wanted to take that burden off the educators and say, okay, we're going to offer a fixed set of crystals that work well. And in terms of demystifying, I think, again, the best way to do it is just building it yourself and just rotating the polarizers and seeing, okay, nothing changes, or doing the Bell measurement and seeing, okay, that's just something, the result is something that's just not classical, and you've done it yourself in the last 20 minutes. And I think that's the best way to demystify entanglement.
Fair enough. I will throw out one anecdote on that note, that I have encountered people in industry that are using this kit and your materials to build their own quantum optics labs as a way to bring their own postdocs and research scientists up to speed quickly by forcing them to go through this and wrestle with the single photon, even coupling it to detectors. I mean, something as seemingly straightforward as that is actually not a trivial task.
Yeah, agreed. And there are some people that bought this outside of like the normal standard curriculum. So we do actually have companies buying this. And I don't think it's too surprising, because, there is a quantum industry emerging, and together with an industry, there's also always a teaching need associated with the employees. And I think it's only going to be more interesting when the race for the quantum computer is decided. So depending on which platform wins, if the photonic platform wins, I think even a lot more companies will purchase the kit. If the neutral atoms win, that's fine as well. I think there's always good reason to look into photonic systems. But yeah, there's definitely a growing number of people in the industry that just want to educate their employees or their customers, whoever, about quantum.
Yeah, absolutely. Couldn't agree with that more. I think this sort of follows on something you already touched on. It's a question about using your own pump laser. So, using maybe an external cavity stabilized diode instead of the multi-mode pump. Is that a relatively straightforward addition or exchange for a customer or an educator?
Yes, I think so. So we actually putting an external cavity diode laser in the kit was our backup plan if the compensation hadn't worked so well. So I had that planned in my project, the time plan. In the end, we didn't need it, but if someone wants to do it, then he will be able to have a single frequency laser. And then, of course, he can leave out the spatial compensators.
Okay.
Sorry, no, the temporal one.
There was an additional question about, so I think this will probably be about the last of the questions that we have time for. There was a question specifically about the temporal walk-off and asking for a little clarification as to the walk-off compensator before the crystal. What purpose is that serving? If you could maybe reiterate that. Yeah,
so essentially, you have to, going into this two crystal arrangement, you have to prepare your polarization states such that, of your pump laser, such that what comes out is gives the proper entangled result. Because, suggest that, for example, your pump polarization state is off a little bit, then you will generate more pairs in the second crystal than in the first crystal. Or while I'm saying it, I realize the formulation isn't super clean. I would rather say the probabilities of the different states are not 50-50 anymore, meaning generation in crystal 1 and generation in crystal 2, but those probabilities are shifted, which again sort of compromises your entanglement a little bit. So you have to properly set your input pump to make sure that the output shows the best possible entanglement. Perfect. And I think that actually rounds up the questions relatively nicely. If we didn't get to your questions, you may receive a follow-up, but I do believe that is all the time we had for today. So I'd like to, again, thanks Jens for the presentation. I'd like to think that I already have a decent view of this, but I learned a lot, so I really do appreciate that, and I'm sure everyone else did as well. For the audience, please do check out the website to view this recorded webinar along with our previously recorded webinars. And with that, I thank everyone for their attendance and hope to see you on the next one.